graphs, networks, and trees. So we're going to be looking at networks and graphs of networks. Now, a network is just a graph. I like to call it towns. These are towns. The little words that we're going to use is a vertex, if it's one, vertices, if it's more than one, so this one has more than one vertex, it has vertices. And we have roads that connect them, which are known as edges here. Now, when we're asked to do the degree of a vertex, we count how many roads or how many lines connect them, how many ledges collect them. So in this case, there are 4. 1, 2, 3, 4. So the degree of A equals 4. We must write D, E, G, and the vertex in capitals, in brackets, and then 3. Okay, this one has 2, 1, 2, 3, 4, because this is a loop and a loop counts twice. Okay, so that's how we do that one. And D, there is 2. Example 1 says, for the graph, find part A, the number of edges. So how many edges do we have? We're just going to count them. 1, 2, 3, 4, 5, 6, 7. There are 7 edges. Number of vertices, 1, 2, 3, 4, 5. A, B, C, D, and E. The degree of each vertex, so the degree of vertex A equals 0. There's no roads connecting it. The degree of vertex B, there are 3 if we count them. 1, 2, 3. The degree of vertex C, now remember we count the loop twice, so we've got 1, 2, 3, 4. The degree of vertex D is 1, 2, 3. And the degree of vertex E equals 1, 2, 3, 4. How many odd vertices does the graph have? Well, the odd numbers are 3, so it has 2 of them, which are B and D, 2 odd degree vertices. A simple graph that does not have any loops, no duplicate or multiple edges, so one edge connects to another one. Degenerate graph, all vertices are isolated. There's no edges in the graph. An isolated vertex, one that's all the way by itself, that's not connected. A complete graph is where every vertex connects to every other vertex in some way. So B connects to all three, the other 3, C connects to the other 3, D connects to the other 3, and so does A. A subgraph is just a part of the bigger graph, subgraph, a part of the other one. So here's 1, graph 2 has A, B, and C, A, B, F, that one there. Graph 3 connects this one in this way, and so does graph 4, A to B. This is not a subgraph because there is no 2 that connect to B, it's only 1. A connected graph means that we are able to get from one place to another, from one vertex to another. A is a connected graph. We have this section connected to this section by this, it's called a bridge, but that's it. But graph 2 is not connected. There's no way we can get from this slot to this slot over here. Example 2, a connected graph is shown on the right. What is the degree of vertex C? Now remember, they asked me it's for the degree, so the degree of C, we're just going to count them. Vertex C, 1, 2, 3, 4. Which vertices have loops? So vertices, there's 2 vertices. B have a loop, and F, because of this one and this one, they're both loops. What is the degree of vertex F? So the degree of F equals, we're just going to count 1, 2, remember we count the loop twice, 3, 4, 5. A bridge exists between 2 vertices. Which vertices are they? Well, there's the bridge from A to C. Draw a subgraph of this graph that involves only vertices A, B, and C. Well, there's my A, there's my B, and there's my C. Okay, now I'm going to go like this and like this. It doesn't matter which one you do from A to B. There's 2, 1 doesn't really matter. See, A to C is only one way. Which of the following graphs are connected? Yes, this one is connected. I can get from A to anyone else and vice versa. D, not connected. Why? Because I cannot get to vertex D. Part C, yes, connected. And part D is not connected. I cannot get from A to D to C to D. Isomorphic graphs. They are graphs that are exactly the same but look different. So they're equivalent graphs. Got the same number of edges, vertices. The corresponding vertices have the same degree and the edges connect to the same vertex. These are example of isomorphic graphs. A connects to C and D. A connects to C and D. A connects to C and D. B to C and D. B to C and D. B to C and D. And so on. They're all the same. Example 4. Identify the isomorphic graphs. Okay, so we need A connecting to D and C. A connects to D and C only. This one connects to B. A connects to D and C. So this one's not. These two are the isomorphic. Graph 1 and 3 are isomorphic. They're the same graph, they just look differently. So I can get from A to the same two vertices C and D on both, B to C and D on both, and C to B and A and D to A and B. Planar graphs. Planar graphs are graphs that do not intersect. Now, this one is not a planar graph the way it looks like, but I can change this as I have over here in the next example, and I've put, instead of this line, I've removed this line and I've put it on the outside here. Now it is a planar graph. Just because it starts off not being a planar graph doesn't mean it's the same. If we can't draw it where no edges cross, then it is not a planar graph. So here, I can remove this one, not a problem, and put it out here. I can remove this one, not a problem, and put it out there. But I still got one connecting from C to E, and when I try and remove it, it crosses over. So this is not a planar graph. Example, show that this graph is planar by redrawing it so that its edges cross. Okay. So the edges cross and they do not cross. So A, B, C, D, E, and F. So I'm going to keep the outside because they're all connecting and they're all fine. I can keep C to E. Now A to D, there we go. I'm going to draw A to D on the outside. So now I've made it a planar graph. Faces of a graph. Okay, faces are how many sections there are. Of course, it has to be a planar graph first. We can't make it into not a planar graph because then we won't have it. So here we've got a section, 2, 3, and then we count on the outside 4. And we have Euler's formula. This only holds true for planar graphs. Okay, and the rule says vertices minus edges plus f has to equal 2. Example 6, consider the connected planar graph shown. So it's telling us it's a planar graph. That means Euler's rule holds true. Write down the vertices, V, edges and faces. Vertices, I've got 1, 2, 3, 4. Edges, I've got 1, 2, 3, 4, 5, 6. Faces, so I've got face here, a face here, a face here, a face on the outside, 4. Verify Euler's rule. Now when it's asking us to verify or show, we start off with the left-hand side, V minus C plus F. Vertices is 4 minus 6 plus 4, which equals 2, which equals the right-hand side as required. Okay, you must make sure you're proving it, you're verifying it, you're showing it. Example 7. For the graph shown at right, redraw the graph into a planar graph. So I'm going to keep these ones exactly where they are. So I've got E, A, D, C, and B. Keep that one, 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 keep that one. But I'm going to go from C to A that way. Part B, verify Euler's rule. Okay, so faces. I've got face. That's 2, 3, and 1 on the outside. So left-hand side is V minus C plus F. Vertices, I can count. There are 5 vertices. Edges, 1, 2, 3, 4, 5, 6, 7. faces, there is 4. 5 minus 7 plus 4 equals 2, which equals the right-hand side of Euler's rule as required. So we have verified it, we've proven it. Example 8. A connected planar graph has 4 vertices, 5 edges. Find the number of faces. Well, because it's a connected planar graph, Euler's rule is true. So we've got 4 vertices, we've got 5 edges. We have to find the number of faces. 4 minus 5 is negative 1 plus f equals 2. So f is going to be 3. 3 faces. Draw it. Okay, so 4 edges. 1, 2, 3, 4 vertices. 5 edges. 1, 2, 3, 4. And 5, I can put it anywhere. I'll just put it over here. And that should give me 3 faces. 1 face, 2 face, and 1 on the outside, 3 faces. Draw it anyway, but it doesn't matter.